Water constantly cycles from Earth to the atmosphere and back to Earth again. Water evaporates from oceans, lakes, rivers, puddles, and even the ground. It then rises into Earth's atmosphere as water vapor, which condenses to form droplets and ice crystals in clouds. When the water droplets are heavy enough, they fall back to Earth as precipitation. Rainwater runs off the surface back to the rivers, lakes, and finally the ocean.
The water cycle, also referred to as the hydrologic cycle, is a never-ending natural circulation of water through Earth's systems. Water molecules move continuously through the water cycle following many pathways. They evaporate from a body of water or the surface of Earth. They condense into cloud droplets, fall as precipitation back to Earth's surface, and infiltrate the ground.
Number 1. What is runoff?
Runoff is water flowing downslope along Earth's surface.
Number 2. What is the source of the runoff?
The source of runoff is precipitation as rain, snow, etc.
Number 3. What becomes of the runoff in the diagram?
Some runoff reaches the stream and the lake. Some accumulates in puddles and eventually seeps into the ground to become groundwater. Some likely evaporates.
Number 4. What determines whether water on Earth's surface will seep into the ground or become runoff?
To seep into the ground, there must be large enough spaces in the ground surface to accommodate the water. If the spaces aren't large enough to open, the water becomes runoff.
Number 5. How does the stream carry its load?
In solution, in suspension, and as bed load.
Number 6. What is a watershed?
A watershed is all of the land area whose water drains into a particular stream system.
Number 7. What separates one watershed from another?
A divide, which is usually a mountain range or a hilly area.
Number 8. Describe the largest watershed in the diagram.
The largest watershed is the main stream's watershed, which covers most of the land shown or all of the area whose water drains into the main stream.
Number 9. What happens to surface water that evaporates?
Evaporated water enters the atmosphere where it condenses into cloud droplets and falls back to the surface as precipitation. Runoff. Water flowing downslope along Earth's surface is called runoff. A number of conditions determine whether water on Earth's surface will infiltrate the ground or become runoff. Soil composition. The physical and chemical composition of soil affects its water holding capacity. Soil that has open surface pores allows the water to infiltrate. The particle size that makes up a soil helps determine the pore space of the soil. There are 3 different diagrams shown, and they show the size from 0 to 1 millimeters in size. So the large grain size is usually greater than that. Fine grain size is much smaller than that, and then mixed grain is somewhere between the two.
When rainfall hits the Earth's surface, one of 2 things can happen. Water can run off the land, or often, with the help of sound land management practices, water can move into the soil to be an environmental positive rather than a negative. The soil itself has an influence on whether water runs off or moves into the soil. Here's a brief explanation of how and why soils transmit water at different rates, and why you should check a soil survey when you're concerned about runoff, flooding, leaching, or other environmental hazards. Water movement in the soil is strongly influenced by soil particle size, or texture, as well as structure and pore size. Soil texture is the relative amount of sand, silt, and clay-sized soil particles. Sand particles are the largest, silt is intermediate, and clay is the smallest. Water moves more quickly through the large open macropores found in sandy soils than the smaller pores of silt, or the much smaller flat-shaped micropores in dense clay soils. Soil structure also impacts water movement. Water moves more quickly downward in soils with granular structure than a soil with platy structure that forces a longer indirect path downward. Other structures include prismatic and subangular blocking. Water is nearly always moving in the soil, and it can be in any direction simultaneously. Gravity is the dominant force that moves water downward. Restricted soil layers of compacted soil or bedrock are among the reasons water moves laterally. Capillary action, the attraction of water into soil pores, can move water in any direction. Gravity is the primary water-moving force in saturated soils, while capillary actions are the primary forces in unsaturated soils. Capillary force is greatest in soils with small pores. Water moves more slowly through these soils. Well, that's a brief explanation of what a soil scientist calls saturated hydraulic conductivity. In simpler terms, the capacity of a soil to transmit water. Since downward moving water carries nutrients and can carry contaminants into underlying groundwater, soil percolation rates are important in choosing sites for septic fields, landfills, and other waste burials, as well as underground storage tanks and other uses. The information is critical for planning soil drainage, irrigation, and tillage systems, as well as other crop management practices. Get the information you need on water movement rates and other soil properties from a soil survey of your area on the web at www.soils.usda.gov.
Three things to remember when talking about runoff are rate of precipitation, that's how fast it's raining, and when it rains too fast, when it exceeds the rate of infiltration, which is absorbing into the ground, the water will become runoff. Vegetation is another. Vegetation can slow the rate of runoff of surface water. Raindrops are slowed when they strike the leaves of trees, blades of grass, and they can trickle down slowly. And the last factor is slope. Water from precipitation falling on slopes flows to areas of lower elevation. The steeper the slope, the faster the water flows. Some surface water flows in thin sheets and eventually collects in small channels, which are the physical areas where streams flow. Rivers that flow into other streams are called tributaries. All of the land area whose water drains into a system is called a watershed. A divide is an elevated area of land that separates one watershed from another. The watershed of the Mississippi River includes many stream systems, including the Mississippi, the Missouri, and the Ohio rivers, along with the Arkansas River and many, many other smaller streams. The Continental Divide marks the western boundary of the watershed. Just how grand is the Mississippi River? The river itself stretches 2,350 miles across the United States. It flows from Lake Itasca, passes through 10 states, and empties into the Gulf of Mexico. But that's not the whole story. Three major rivers empty into the Mississippi: the Missouri River, the Arkansas River, and from the east, the Ohio River. And tens of smaller rivers and streams empty into those three rivers. Together, the drainage system covers 1.24 million square miles, which is about the same square mileage of 2 Alaskas. It crosses over 31 states and 2 Canadian provinces. It's the largest in North America and the fourth largest in the world. This watershed helps produce 92% of the nation's agricultural exports and 78% of the world's exports of feed grains and soybeans. Plus 60% of U.S. grain exports are shipped on the Mississippi. Without this watershed, the Mississippi River would not be the resource it is today. Stream load. The material that the stream carries is known as the stream load. Stream load is carried in three ways. First one is materials in suspension. A suspension is a method of transport for all particles small enough to be held up by the turbulence of the stream's moving water. A stream's bed load consists of sand, pebbles, and cobbles that the stream's water can roll or push along the bed of the stream. And last is when water runs through or over rocks with soluble minerals, it dissolves small amounts of the minerals and carries them away in solution. Now, this is taken on a GoPro, and it is a small area of a river in Alaska. This is only 5 inches of water, but it's moving very quickly. And as it's moving, you can see that the bed load is actually moving. Most people think that the bed load is not moving under the water, but when the stream velocity is high enough, this does happen. There is also things in solution, and every so often you will see some cloudy areas, which is suspension. The carrying capacity of a stream is the ability for it to transport material, referred to as the carrying capacity, depends on both the velocity and the amount of water moving in the stream. Discharge is a measure of the volume of the stream water that flows past a particular location within a given period of time. Stream discharge is a product of the stream's average width, as you see on the diagram on the right, the average depth, and the velocity of the water.
Over the past 100 years, no other natural disaster in the U.S. has caused more death and destruction than floods. They can happen any place, any day, any time. And they will likely only get worse. As people cluster around coastal regions and floodplains, our growing population will confront the awesome power of water. For thousands of years, farmers have depended on seasonal floods. The waters irrigated their crops and fertilized their lands. Today, excess water is channeled into reservoirs and power hydroelectric dams. But when water levels rise suddenly, far more than the ground can absorb, a flood occurs. Flash floods are a perfect example. Sudden storms unleash a torrential downpour. The runoff moves with surprising force. At a depth of 2 feet, the water can push aside a car. In fact, half of all deaths from flash floods involve vehicles. But floods occur in many other ways. Heavy rains and thawing snowfall can overwhelm rivers. Storm surges caused by hurricanes and tsunamis inundate the coastline. Landslides and mud flows can displace large volumes of water. Dams break, levees fail. In the Great Mississippi Flood of 1993, several of these factors came into play. Over 10,000 square miles of the Midwestern United States were overwhelmed with rain. In a cruel twist, the earthen dams known as levees along the upper Mississippi River forced the water to flow downstream faster and stronger. Communities further downriver were hit with the full brunt of the Mississippi. 2/3 of all the levees were breached. Though towns rallied to protect their lives and livelihoods, the damage was still immense. Over $10 billion in damages, 56,000 homes flooded or destroyed, and some 50 people were killed. At the start of this century, another powerful flood wreaked havoc, this one coming from the sea. The storm surges of Hurricane Katrina submerged 80% of the city of New Orleans. Over 1,800 people died in the floods. The damage has been estimated at over $80 billion. In some ways, the New Orleans disaster was unique. Much of the city lies below sea level, and despite years of warning, the city was woefully unprepared to handle a breach of the levees which kept it dry. But we are still vulnerable. Sea levels may rise, coastlines could erode, rain patterns might change, snowpacks could melt, and then the waters would rush in.
A flood occurs when water spills over the sides of a stream's bank onto the adjacent land. The broad flat area that extends out from the stream's bank and is covered by excess water during the flooding is known as the floodplain. When rivers overflow their banks, the floodwater deposits sediment. Over time, sediment accumulates along the edges of the river, resulting in a natural levee or a natural dam, something to keep the water from flooding again. Flood stages. When the water level in a stream rises higher than its bank, the river is said to be at flood stage. The flooding of a small area is known as an upstream flood. Heavy accumulation of excess water from large regional draining systems results in downstream floods.
Good afternoon, I'm Hasiel Cordoba. We will get to our detailed forecast in a few minutes. First, we have a team of reporters covering some of the areas already being hit hard by ECS. And we're seeing flooding and some road damage in Northampton County. And that's where we find WFMZ's Allie Reed. Allie, how's it looking out there?
This is by far the worst flooding that I've seen throughout the morning and into the afternoon here. If you take a look at this road, completely flooded, okay? We're talking, you can't even step foot into that lane over there, okay? The people in the area have completely moved their cars out of the street to make sure that they're staying as safe as possible. I talked to a man up on the hill over here who tells me this isn't even the worst that they've seen in this area over the last couple of years. They say back in 2004 when Hurricane Ivan hit, he said that he could see flooding all the way up into their house. It was getting into their basements, flooding out total areas. So what you're seeing right now isn't even the worst of what this area typically gets during hurricane season. Now, on top of that, we've spoken to people right here in this front lawn who says that they're pretty close to getting that flooding in their basement as well. I mean, this is completely coming up to the area on their lawns, completely covering every aspect of this area here. Now, this is just one portion of the area that's experiencing flooding as of this morning. If we take to some video that we saw earlier, around 10 o'clock this morning, we saw an Amazon delivery truck over in the lower Saucon area in Steel City go through a landslide, go off onto the side of the road. It was pretty crazy scene over there. Now, that person that was driving the truck, I'm told by police officers that he is doing okay and was able to safely get out of that truck. Now, on top of that, we've had other flooding throughout the area, both in Lower Saucon and in Bethlehem Township. So that's been pretty crazy as well to see that. The creeks have been a big one, too, have been completely flooding roads. We even got viewer video earlier that was over in the area, too, over in Bethlehem Township, just a few blocks down from where we are right now going live. So we've seen a little bit of everything as of this morning. But again, this is pretty incredible to see this here. I mean, the neighbors here, they say they are frustrated that this has happened so many times. And now we're going into another year of hurricane season. They say this is just crazy to be able to see this. I mean, I'm seeing it with my own eyes. I wish that some some of you could totally understand how deep and how thick and how rapid these waters are here. They even said a couple of years ago there was a 14-year-old that had died right in this area because of how fast this water had been going. So again, this is we're staying as safe as possible, being up as high as we can in this area. But again, this flooding, especially if they're saying this is the peak right now, I don't know, guys, this is pretty bad. And as we're talking right now, as we're going, I mean, we have to step back here because of how bad this flooding is getting. It is moving at such a fast pace. But of course, this isn't the only flooding in the area. We're going to be sending it to our other reporters now. So for that, I'm going to send it off to that. But for now, live here in Bethlehem Township, Ali Reed, 69 News, sending it back to you in studio.
That footage was from this past summer, 2020. The region where water first accumulates to supply a stream is called the headwaters. Falling precipitation accumulates in small gullies at higher elevations and forms briskly moving streams. Moving water carves a narrow pathway into sediment or rock called the stream channel. The stream banks hold the moving water within them. When small streams erode away the rock or soil at the head of a stream, it's known as headward erosion. The headward erosion of Stream A cuts into Stream B and draws away its water into one stream in a process called stream capture. It's also called river piracy.
Geoscientists spend their lives studying features in nature that move very, very slowly. Glacial melt, plate tectonics. These things take their sweet time to develop, so when an entire river vanishes in just 4 days, it's safe to assume geoscientists are going to freak out. A paper recently published in Nature called this very sudden disappearing act river piracy. Sadly, there were no pirates actually involved in the making of this study, but river piracy, or its less exciting name, stream capture, is a geomorphic phenomenon where one river captures and redirects the flow of another river. Luckily for us, NASA was watching when this happened. Check this out. In 2015, a team of scientists observed that the Slims River in the Yukon was, quote, swift, cold, and deep, flowing from one of Canada's largest glaciers north to the Bering Strait. Then in 2016, NASA took this picture. The scientists on the ground came back and the river was completely different. Its water flow was at a near screeching halt. It looked more like a, quote, long, skinny lake, and they could see that the water level was dropping by the day. What had happened was, a tall canyon had formed at the end of the nearby glacier, rerouting the meltwater from the Slims to the Kaskawalsh River, joining the Alsek River south. Basically, the Slims River was stolen by another river and it just completely changed course. This shift is affecting fish populations, wildlife, lake chemistry in the area. Even sheep are changing their grazing patterns, which it sounds kind of but think about how this could affect everything else. Land degradation and lack of fresh water can impact billions of people globally. Plus, there may be more consequences that we hadn't even thought of yet. This is the first time in modern history that scientists have actually seen a river redirect like this. A whole river was going north, now it's going south. That's huge. And why? You probably already know why: man-made climate change. But not global warming as a whole. Instead, one of its many facets, glacial retreat. Glaciers are these massive bodies of snow and ice that change in response to temperature and precipitation. When a glacier starts to retreat due to high temperature or less snowfall, glacial melt will outpace new accumulation of snow and ice. This affects the availability of fresh water for animals, plants, even humans. This connects to the river piracy in the Yukon because the massive Canadian glacier that fed the Slims River is in retreat, thanks to a cold period centuries ago called the Little Ice Age and warming due to greenhouse gases. Now, while this study was just one glacier, and we shouldn't generalize too much across the planet, glacial retreat is a worldwide phenomenon. Glaciers in the Himalayas, Andes, Alps, and Rockies are all backpedaling at greater speeds in response to our global changing climate. Of course, glacial melt is happening in some of the farthest corners of our planet, and only a small number of communities are directly affected, for now. So while global warming is a multi-century process, things can happen quickly. Consequences of global warming and climate change are being seen now, and huge parts of the environment can change course in just a matter of days. And no one knows what this will mean for the future. So if all these glaciers keep retreating, what happens if all the world's ice melts? Check out this video here to learn more about that. What's your favorite piece of evidence that climate change is happening now? Let us know down in the comments. Like this video and make sure you subscribe for more.
The energy of a stream comes from the movement of water down a slope. The slope of a stream channel is called the stream gradient. The gradient of the stream depends on its base level, which is the elevation at which it enters another stream or another body of water. The height of a stream above its base level determines how much downcutting energy the stream will have. Downcutting energy is the energy to actually deepen a stream and make it deeper and deeper. Meanders. A meander is a bend or curve in a stream channel caused by moving water. Water moving along the outside of a meander curve experiences greater velocity within the meander and erodes the side of the stream bed. Along the inside of the meander, the water moves more slowly and deposition is dominant, because what happens is on the inside, as the water's slowing down, it doesn't have as much energy, so it can't hold as much material, so the material falls back down to the bed. After enough winding, it is common for a stream to cut off a meander and once again flow along a straighter path. The blocked off meander becomes what's called an oxbow lake, which eventually will dry up.
2-minute geology, the 2-minute geology. Hello, young people. Entrenched meander. This is the Yakima River just south of Ellensburg, Washington. Meanders are a feature of old age, these sweeping curves of the river. As rivers age, they develop more and more exaggerated meanders. We know this by flying over the Mississippi River system. And we see all stages of meander development back there. Eventually, the meander becomes so exaggerated that that curve is abandoned and an oxbow lake is formed, and the channel becomes straight again. We can only develop these curves when an area is flat, like back east at the Mississippi. And here we've got these exaggerated curves as well, which means central Washington used to be flat. But there's a twist. This place isn't flat anymore. This is a deep canyon system. So to understand that twist, how about we get up on that rim and get a big picture view of the Yakima River Canyon. Let's go up there. High up above the Yakima River, on the rim of the canyon looking down, there's one of our meanders. We know about meanders. The meanders got established when the area was flat, a subtle curve becoming a more exaggerated curve. But then we froze the position of this meander and we entrenched it. Entrenched meanders tell us that the land is lifting against the river. The river wasn't up here and was cut down. We're sure that the river has been down there for millions of years, and the land has been lifting against the meander, against the river. The river's been cutting, matching an uplift rate of the bedrock, basalt layer after basalt layer, exposing themselves on the way up. The future of this meander is not more exaggerated meander, development of an oxbow lake. Instead, the future of this curve is more cutting, because the uplift continues here in central Washington. Entrenched meanders, just south of Ellensburg, Washington.
Number 1, in a straight stream channel, where does the water have the maximum velocity?
If you look at the bottom, the maximum velocity is in the center of the channel. The reason the maximum velocity is in the center of the channel is there's less friction in water than where water's touching the stream bank or the bottom bed.
Number 2, in a straight stream channel, where does the water have the minimum velocity? Explain your answer.
The minimum velocity occurs along the sides and the bottom of the channel where the water experiences friction as it moves against the land.
Number 3, what is a meander?
It's a bend or curve in a stream channel.
Number 4, in a meandering stream channel, where does the water have the maximum and minimum velocity?
As you can see down to the left, the velocity of the water is at the maximum along the outside of the meander and minimum along the inside of the meander.
Number 5. In a meandering stream channel, where is the deposition dominant?
Deposition is dominant along the inside because, as I said, the minimum velocity is there. When the river is moving slower, that means it can't hold as much material, and that material will deposit down on the bed.
Number 6. What is the narrow pathway in which stream water flows?
The stream channel is the pathway in which water flows.
Number 7. What holds a stream's moving water within its narrow pathway?
The stream banks hold the water in the channel.
And lastly, number 8. How does an oxbow lake form?
An oxbow lake forms when a stream deposits material along the adjoining meander, cutting off the meander and blocking its water supply. Visualizing erosion and deposition in a meander. The meanders of a stream are accentuated by differences in velocity in the water. Deposition of sediment. When the stream loses velocity, like I said, on the inside of the meander, inside the curve, they lose some of the energy needed to transfer sediment, and deposition of sediment occurs. An alluvial fan is a fan-shaped sloping depositional feature that forms when water flows down a steep slope onto a flat plain. Alluvial fans are composed mostly of sand and gravel, so larger particles. Deltas. The triangular deposit that forms when a stream enters a large body of water is called a delta. A delta deposits are usually layers of silt and clay particles, and that's what you can see in the brown areas. That is the clay and the silt. Those are the smaller particles. They do not need as much energy, so this is really when the stream starts to stop. So when it starts to stop, that's when even the smaller particles will start to settle to the bottom. Rejuvenation is when a stream will resume the process of downcutting. Now, the man told you in the video, downcutting is when the water doesn't have anywhere to go, so it cuts down into the channel and makes it deeper and deeper. This causes an increase in the velocity because what you have is you have more area to cover, so the water can move faster. And once the stream will cut downward, it will then cut into existing meanders. If you look just about in the middle of the system, if this is flowing from right to left, that area where it first curves back down towards the bottom of the slide, that area is going to be the part that's cut out, and eventually it will close off, and the whole bottom section of that will turn into an oxbow lake, and it will then continue up and to the left. Origins of lakes. Natural lakes are bodies of water surrounded by land, but they form in different ways and in surface depressions and also in low areas. Some lake forms when a stream flow becomes blocked by sediment from landslides or other sources. Other lakes, such as moraine dam lakes, cirque lakes, and kettle lakes, have glacial origins, meaning they came from glaciers. Lakes can undergo change. A depression that receives more water than it loses to evaporation or use by humans will exist for a long period of time. However, over geologic time, most lakes are temporary because what happens is over time, more sediment, more filling, so eventually the lake will fill up and have shallower and shallower areas. Lakes undergo change, the process by which bodies of water become rich in nutrients that stimulate excess plant growth is called eutrophication. Although eutrophication is a natural process, it can be sped up with the addition of nutrients such as fertilizers that contain nitrogen and phosphorus.
What's going on, guys? Chemist Nate coming to you live from Lamoureux Park in Scarborough, Ontario. My question for you is, what's the difference between a lake like this and a lake covered with algae like this? The answer is that the lake covered with algae has undergone eutrophication. Eutrophication is an overgrowth of algae or cyanobacteria or phytoplankton, whatever it takes, to cover a lake entirely with some kind of photosynthetic stuff. You know, plants. Nutrients have come from somewhere and have flooded into the lake. Farmers are fertilizing their fields, making sure all their crops grow, but then the rain comes, and the rain washes the phosphorus and the nitrogen and the potassium and all the other stuff in the fertilizers back into the lake. And all the stuff plants need to grow dissolved in the water in the lake. So what happens? Plants grow inside the lake, like algae, cyanobacteria, and phytoplankton. They cover the entire lake. Large sheet of green goo. Large amounts of green goo covering the lake prevent light from getting into the lake, and that means that plants that are already on the bottom tend to die because they're not getting light. When these things decompose, they consume oxygen, and what you get is a state of hypoxia, which is not a lot of oxygen. And if it continues, you can get to anoxia, which is no oxygen at all dissolved inside the lake. If fish don't have oxygen to breathe, they will die. Just one nutrient, phosphorus, flowing into the lake can cause everything in the lake to die. There are a few different things that this eutrophication can cause in a lake. Number one, the lake doesn't look as pretty as it should. Number two, it can absolutely obliterate the fish and animal populations inside the lake because there's no oxygen dissolved inside of it. Number three, because some of the fish have disappeared, other species can come in and take over. Here's another problem. That green goo that forms might even be toxic itself. We've isolated like 12 or 15 different toxins from these kinds of bacteria and algae. Problem is, these toxins get into the water, or fish eat the algae, and then they get toxified, and then what if you eat the fish that ate the toxic algae? It's just a huge problem all around. We know that in lakes like this one, it's phosphorus that causes the problem. Because back in the day, in something called the Experimental Lakes area up in northern Ontario, they took a lake and literally divided it in half. They put up this barrier so that one half had normal conditions and the other half, they added phosphorus to it. The side that had the phosphorus added to it, huge amount of algae. The side that didn't have phosphorus added to it, perfectly normal like this one. Where are the nutrients for eutrophication coming from? Two categories: point sources and non-point sources. Point sources are one place, we know exactly where it's coming from, and it's actually pretty easy to find and eliminate those. Say a chemical company just dumping fertilizer into the lake through one of their runoff pipes. All we have to do, plug the pipe, done. The worst problem is non-point sources, where you can't tell exactly where these nutrients are coming from. If you have 2 or 3 farmers' fields around the same lake, the farmers are all going to apply fertilizer. Each time it rains, the fertilizer gets washed away, and you wash a little bit into the lake, and then a little bit more, and then a little bit more, and some of the fertilizer can seep through the soil in the hills and then end up in the lake from the bottom. Nutrients can come from a whole bunch of different places if they're non-point sources. Who's going to take responsibility for that? Certainly not me. Long story short, too much algae equals bad. 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 We don't want that much algae in a lake.
Freshwater wetlands. A wetland is an area that is covered with water for only part of the year. Wetlands include environments commonly known as bogs, marshes, and swamps, which have certain soil types and support specific plant species. Wetlands play a valuable role in improving water quality. They serve as a filtering system that trap pollutants, sediments, and pathogenic bacteria contained in water sources.
What makes a wetland a wetland? The simplest answer is water. Wetlands are found throughout the world wherever land and water mix. There are many different types of wetlands, but a wetland is not a puddle, nor is it a lake, pond, stream, or river. And while water is certainly important, wetlands are also defined by their soils and plants. Wetlands are areas of land saturated with water. This means that wetlands hold and absorb water similar to a sponge, but not all wetlands are always saturated. The movement of water to and from a wetland is known as its hydrology. While some wetlands are almost always underwater, others are rarely flooded. Many people think of wetlands as muddy, but wetlands can often look dry for much of the year. So all wetlands are wet, but not all wetlands are always wet. Wetlands also have hydric soils. These are frequently flooded or saturated soils. Most non-wetland soils are full of oxygen, but in hydric soils, water replaces this oxygen, changing the soil chemistry. Did you know this is why wetlands often smell like rotten eggs? Wetlands are also defined by their plants. Most plant roots and soil bacteria need oxygen to survive, so in hydric soils they will quickly die. But not wetland plants. Wetland plants, also called hydrophytes, can survive and grow with limited oxygen in hydric soils. So all wetlands are made up of water, hydric soils, and hydrophytes. But are all wetlands the same? Many people think of wetlands as marshes, but there are actually many other types of wetlands. Some other common types include swamps, bogs, and fens. A marsh is a regularly flooded wetland with soft-stemmed vegetation. Coastal marshes exposed to tidal flooding are called salt marshes. Few plants can tolerate this harsh environment. Salt marsh cordgrass is one of the most common salt marsh plants. Freshwater marshes have much greater plant diversity. Some of the many plant species found in freshwater marshes include cattails, marsh hibiscus, and pickerel weed. A swamp is a forested wetland with woody plants such as trees and shrubs. Sometimes swamps are completely flooded, but many swamps are often just saturated or muddy. Some of the forested wetlands found in the United States include bald cypress swamps in the southeast coastal plain, mangrove forests along southern Florida and the Gulf Coast, and red maple swamps in the northeast U.S. Bogs are mossy rainwater-fed wetlands with a variety of evergreen trees and shrubs. Many other beautiful and interesting plants such as cranberries, orchids, and even the insect-eating Venus flytrap are found in bogs. Bogs are well known for their spongy soil called peat. Peat forms from partially decayed plants and is common in many wetlands. Fens are also peat-forming wetlands, but they are groundwater-fed and look more like meadows with many grasses, reeds, and wildflowers. Wetlands were once viewed as stinky, insect-ridden wastelands, but we now know that wetlands provide many important benefits. Wetlands act as a natural filter to provide clean water. They help prevent flooding and maintain river flow. And wetlands provide critical habitat for fish and wildlife, as well as beautiful scenery and opportunities for recreation. Wetlands are able to provide these benefits because of the movement of water to and from the wetland. Without wetlands, or the hydrology that supports them, many of these important ecosystem benefits could be lost.
Number 1. What sources supply water to the lake?
You look, you see precipitation, runoff, and the spring underneath it.
Number 2. Describe the characteristics of the young, healthy lake.
The lake has high dissolved oxygen content and low waste product content. It supports a variety of abundant organisms, and its plants contribute to oxygen through photosynthesis.
Number 3. What is eutrophication?
Eutrophication is a successional process that begins with the addition of nutrients and continues with the filling in of a lake as a result of excess organic growth.
Number 4. How does the dissolved oxygen content of the lake change during eutrophication?
It drops. Simple as that. It drops.
Number 5. How does eutrophication speed up?
The phosphates and nitrates picked up by runoff enter the lake, resulting in excess algae growth, as the man in the video showed you over and over and over.
Number 6. What other changes occur in the lake as eutrophication continues?
Sediment and waste products build up, filling in the lake. Algae thrive, excess growth occurs, and many organisms die and decay.